All right, this is the second part or the second lecture on probability and state standards number 1 and 2. In the first one, we talked about independent events and dependent events, which is conditional probability. We talked about the multiplication rule. We talked about the addition rule, but we only did the mutually exclusive case. And we haven't done complementation yet, so we're going to finish off and include those parts. But first, I would like to remind you of the addition rule. Two events are mutually exclusive if they cannot happen at the same time. So when you roll a standard fair six-sided die, you can't get a 1 and a 3 at the same time. When you flip a coin, you can't get a heads and a tails at the same time. Those would be mutually exclusive. And so in the first section, we did the special case of the addition rule. In this particular lesson, we're going to continue on and do the regular full addition rule with inclusive events. And so to look at that, let's take this particular example. We are taking a card, it's chosen at random, from a standard deck of 52 playing cards. What's the probability that it's a red or face card? Now again, we're only taking one card. So don't worry about dependent or independent, if we're putting it back or not. We're just taking one card. We want to know what's the probability that the card is red or it's a face card. Now, in case you forgot, face cards would include kings, queens, and jacks. And this is actually not mutually exclusive like we did in the first episode. This one is inclusive because there are some face cards that are red. In fact, there are 6 to be precise. We know that there's a suit of hearts and diamonds that are both in red color ink. So there would be king, queen, and jack of hearts, king, queen, and jack of diamonds. Those would be the 6 red face cards. So we're going to use the full addition rule here. So the probability of event A or the probability of event B is the probability of A occurring plus the probability of B occurring minus the probability of anything that could happen at the same time, which in this case is that it is red and a face card. So let's write this out. We want the probability of a red or face card. That's equal to the probability of a red plus the probability of the face card minus the probability of drawing a red face card. And in this case, let's take a look at a red or a face card. So there are 26 red cards, as we said, in the deck of cards. We said this in a previous lesson. Half of them are red, half of them are black. So there are 26 favorable outcomes for a red over 52 possible outcomes because there are 52 in the deck of cards. And then face cards, there are 12 face cards. There's a king, queen, and jack of hearts, diamonds, spades, and clubs. So 4 suits times 3 face cards gives us 12 favorable desired outcomes for a face card out of 52 cards, because there's 52 in the deck. And then we need to subtract the 6 cards that are both red and face cards. So the probability of drawing a red face card, there are 6 of those out of 52 cards in total. So when we do this, 26 plus 12 minus 6 is 32 over 52. And we reduce, we have an 8 out of 13 chance, 0.615 or 61.5% chance that the one card we take from the deck is either red or a face card. All right, another one we haven't looked at is the concept of at least, or at most. We're going to do an example of at least. So in this situation, there are 6 women and 7 men on a committee. They want to form a subcommittee of 5 members being randomly selected from the original committee. What's the probability of at least 3 women being on this committee? Now, the phrase at least means the committee can have 3 women, 4 women, or 5 women. So we've got the addition rule here. Probability of at least 3 women is the probability of having 3 women on the committee plus the probability of having 4 women on the committee plus the probability of having 5 women on the committee. Now, that's what at least 3 means. Now, what we're going to do is we're going to figure out the choosing or selecting of that. So in this case, if we have 3 women, we have to have 2 men on the committee, so we have 5. There are 6 women to choose from, and we would choose 3 in this particular situation. So let's just focus on this fraction on the left here. And then for men, there are 7 men to choose from, and we're going to choose 2 of them. And so 6 choose 3 times 7 choose 2 is the numerator of our first fraction. And our denominator is there are 13 people involved, and we're going to choose 5 of them. Now that's the probability of having 3 women. Next we move on to the probability of having 4 women. So there are 6 women to choose from. We're going to choose 4 of them, which means that from these 7 men, we're only going to choose 1, and we need to multiply those together for our numerator of the probability of 4 women. And there are still 13 people to choose from, and we're only going to choose 5. And then in the last situation, what if all 5 women were on the committee? So we have 6 to choose from, and we're choosing 5, and that leaves no room for any men on the committee, so there would be 7 men to choose from, and we wouldn't choose any of them. That would be our numerator for the probability of 5 women. Denominator, again, there are still 13 people, and we are choosing 5 of them. Now, to try to avoid getting messy calculations, I did these off to the side. Technically, if you want to know, I used my calculator. So 6 choose 3 is 20. 7 choose 2 is 21. We're going to have to come back and multiply that. For our numerator for 3 women, the favorable or desired outcome, having 3 women, 2 men. And then denominator is 13 people choose 5. Did that on my calculator. There's 1,287. In the next case, we had 4 women and 1 man. So 6 choose 4 is 15. 7 choose 1 for man is 7. We will multiply those together. Our denominator is still 13 choose 5, which is 1,287. And then in the last scenario, there are 6 women. We're going to choose 5, which is 6. 7 men choose 0, which is 1. We'll multiply that for our numerator. And our denominator is still 1,287, which is 13 choose 5. Since we have the same denominator, we're going to be adding in just a moment, but first we need to multiply our numerators. So in the 3 women case, 20 times 21 is 420. In the 4 women case, 15 times 7 is 105. And in the 5 women case, 6 times 1 is 6. Denominators are all the same, so keep it. Add the numerators, which gives us 531 out of 1,287. Now, let's reduce both the numerator and denominator by 9. That gives us a 59 out of 143 chance, or 0.413, or for if you like percents, 41.3% chance that at least 3 women will be on this subcommittee. All right, the next thing we need to look at is the concept of complement. So we'll get a few little definitions out of the way first. The sums of all the probabilities of a sample space is 1. So if you had heads or tails, probability of a head is 1/2, probability of a tail is 1/2. Add them together, 1/2 plus 1/2 is 1. Rolling that standard fair sided, 6-sided die, probability of getting a 1 is 1/6, 2 is 1/6, 3 is 1/6, all the way out to 6 is 1/6. Add 1/6 to itself 6 times, you get 6/6 or 1. So the sum of all probabilities in any sample space is 1. The complement, now here's our definition. The complement of event A is the set of all outcomes in the sample space that are not part of A, which means the complement of event is the probability of that event not happening. And here's how we calculate complementation. The probability of the complement of event A, which can be written in a few different ways. Probability, we can put the word not, A, is going to be 1, which is the sum of all probabilities in that sample space, minus the probability of that event occurring. And in this case, that will simplify this particular example. If we have a standard fair 6-sided die, what's the probability of not rolling a 2? Well, you could do the addition rule and figure out the probability of rolling a 1, a 3, a 4, a 5, a 6, and adding them all together. But it would be much easier to find the probability of rolling a 2 and subtracting that from 1. So the probability of not 2 is 1 minus the probability of rolling a 2. As we said in a previous lesson, there's only 1, 2 on that 6-sided die. So that favorable or desired outcome would be 1. And there are 6 possible outcomes on a 6-sided die. So the probability of rolling a 2 is 1/6. Now, here's another notation. And I've seen all kinds of notations. Instead of writing the word not to, we'll put that little line over the 2, not quite the line segment line, but it looks like it, which is the probability of not a 2. I've also seen people write a C, kind of where the exponent would go, meaning the complement. All right, let's get back to our calculations. 1 minus 1/6 is 5/6, which as a decimal is 0.833. So you've got an 83.3% chance of not rolling a 2. All right, in our next example, we're going to look at complements. So let's take a look at this weather forecast. On a certain day, the chance of rain is 40% in Chicago and 20% in Los Angeles. Assume that the chance of rain in the two cities is independent. What's the probability it will not rain in either city that day? All right, so let's write this out in words. The probability of not raining in Chicago or LA is the probability of it not raining in Chicago times the probability of not raining in LA. As we look at that and kind of expand it, let's find out the probability of it not raining in Chicago. They say the probability of it raining in Chicago is 40%. So not, the complementation of that, would be 1 minus the probability of raining in Chicago, which they told us is 40%, or 0.4 in this case. 1 minus 0.4 is 0.6, which you can think of as 60%. So when the forecaster says, you know, there's a 40% chance it'll rain, well, that means there's a 60% chance it will not rain. We all are familiar with that concept. All right, let's come back and fill in the details for the Los Angeles component. Probability of it not raining in Los Angeles is 1 minus the probability of it raining in Los Angeles, which we're going to take that 20%, write it as a decimal, 0.2. 1 minus 0.2 is 0.8. So yes, next time the forecaster said there's a 20% chance of rain in Los Angeles, of course that means there's an 80% chance it will not rain. All right, now that we've calculated independently for each city the probability of it not raining in Chicago, not raining in LA, let's say you're going to fly from LA to Chicago or vice versa, we want the probability of not raining in Chicago times the probability of not raining in Los Angeles. So that's going to be 0.6 times 0.8, which is 0.48. So there's a 48% chance that if you're going from one city to the other in the same day, you don't need an umbrella or any other kind of rain gear. All right, let's look at another example of a drawing card. So let's say that a card is chosen at random from a standard deck of playing cards. Find the probability of drawing a jack or a red card. And again, we're only drawing one card. Or is your clue that it's the addition rule? Now you've got to decide if it's mutually exclusive or inclusive. So to ask that in another way, are there any jacks that are reds? And the answer to that is yes. Okay, there are some red cards that are jacks, 2 of them exactly. There's the 2 of hearts, 2 of diamonds. The jack of hearts and jack of diamonds. So we've got 2 jacks that are red. So it's not mutually exclusive, it's inclusive, and we're going to use the general form of the addition rule. So the probability of event A or event B is equal to the probability of event A plus the probability of event B minus the probability of event A and B occurring. Now, to fill out event A and B, what we're looking for, event A would be drawing a red card, event B would be drawing a jack. So the probability of a red plus the probability of a jack minus the probability that is red and a jack both. So in this case, as we said, there are 26 red cards again. So that's our favorable outcomes for event A. 52 cards in the deck, so 52 possible. Again, we're only taking one card. There are 4 jacks in the deck, so that's 4 out of 52. We are only taking one card, so it's not what we're getting on the second card. It's not dependent. So 4 out of 52 chance of getting a jack, and there is a 2 out of 52 chance that it is red and a jack both. So they have the same denominator. We will add the numerators. 26 plus 4 minus 2 is 28. And that reduces to 7 out of 13, or 0.538. Or you've got a 53.8% chance that you draw, when that one card you draw, it's either a jack or it's a red card. All right, so just to quickly summarize, we have officially finished State Standard 1 and 2. We've talked about independent events, dependent events, which is also known as conditional probability. We've talked about the multiplication rule, the addition rule, and we've talked about complementation.